Okay. So the first one, how many think this is correct? It's correct, right? Dislocations are linear defects. There are irregularities within the material and within the crystalline structure. So this one is correct. How about B? Dislocations generally reduce material's ductility. Is this true? Why not?
Because it's easier to slip.
Exactly. So last time we discussed that dislocations are actually behind the ductility in most metals. That's what makes the material to have plastic deformation. So this is not true. But let's look at C also. Dislocation decrease both the compressional and tensile and compressive strengths. Why is this true? Dislocations are defects, remember? And when we have defects, tensile strength decreases in brittle materials. But in metals, whether you are stretching or pressing, the material is failing in shear, it slips. So if you have dislocations, you are going to have easier slippage, lower strength. Makes sense? Convinced? And how about D? We talked about alloying. You remember the tractor I showed you? When we have alloying, the foreign atom would not let the slippage to happen as easily. Because of that, the strength is going to be higher. I'm sorry. And the ductility is going to be lower. So it prevents the slippage and increases the strength. So this all looks good. Okay, the second problem, like number 8. What is the answer? This one kind of you need to look it up or you remember. What is the answer? No. So this is asking which one has hexagonal closed path structure. You have to remember. In the class, I have told you that zinc and titanium, they both have. So, and this would be the only answer which has both of them. Actually, magnesium is the only one which doesn't have. And number 15, before you work on this annealing, I think I quickly explained this last time, but it is the opposite of quenching. So what was quenching? What does it do? Look it up in your notes and then tell me what quenching was and what it does to the material, how it changes metals' properties. Look it up. It's in your notes. Does anyone remember what it was? Wants to explain it? This is true, correct. So, quenching, the process is when you have molten metal and very quickly you actually cool it down, very quickly. And then the material doesn't have time to grow large grain size. So you have a small grain size. And why would we do that? Do you remember why would we talk about it? You have an exam next week. It's time. So why did we talk about quenching? Why? Just like that? Exactly. In the context of strengthening, in the context of hardening metals, we talked about it. Because we said when you have more grain boundaries, they prevent a slippage. So you are going to have higher strength. Annealing is the opposite. So you can imagine that you have the molten material and you let it cool down very, very slowly, very slowly. So what do we expect? We have a lot of time to have large grains, so grain growth. What else? What do you think in terms of toughness? Do you think the material becomes tougher or it becomes less tough through annealing?
Less tough?
Why?
Because it's the opposite of quenching, and quenching makes it more tough.
Quenching increases the strength. And typically when we do that, we lose ductility. So, what is the definition of toughness?
The area under the stress strain.
Exactly, the area under the stress strain there. So, if you use annealing, if you pull the material down slowly, maybe you don't have that much strength, but you increase ductility. So you would increase toughness. Okay? Another thing that happens during annealing is internal stress relief. Because you are cooling down the material slowly, so the internal stress will relieve itself. So actually the answer is B. And these are from FE exam again, these questions. The materials section. Any questions about this small kind of a quiz, these questions? Okay. So we can move to steel. So I told you that from today on, basically each packet will be on a different material, which matters to us as civil or architectural engineers. From now on, more and more we can rely on the textbook because we are going more from the more science part of the course to the engineering. Chapter 3 of the textbook can also look at the additional reference that is on the syllabus and chapters 9 to 11. I had asked you to watch a video on steel production, so we don't spend too much time on the details. This is a diagram which kind of summarizes steel production. The first step is pretty much starting with the raw material, iron ore. You enrich it to have the high carbon pig iron, and then you are going to have pig iron to change it to steel, and afterwards you are going to make steel products. And you see that there are different ways to do that, and the types of products that we are interested in are mostly made by hot rolling, as you can see here. So if you want to summarize the steel production, you can consider 3 steps. And these 3 steps, I don't know how you categorize this in the diagram that you just submitted. These are kind of the 3 steps that I see in the production, where you start with the raw material, iron ore, and then you enrich it to get high carbon pig iron, and then you refine pig iron, reduce the carbon to go from pig iron to steel, and finally you make the product. Very strange to me. So now we look at each each of these steps a little bit, very briefly, but so we have a good summary. So the first step is going from ore to pig iron. You increase the iron content to about 65%, and this is done. And then you are going to use coke or coal in blast furnace. I guess you saw this in the video, the blast furnace, in order to release iron here. Another important aspect that you saw in the video is the use of limestone powder. So it's important to pay attention to that. And it is used to trap the impurities. So you are going to have them kind of skimming off the top of the molten material. And then you have the molten rock at the bottom collected. This is kind of a summary of the first step. So the second step is basically reducing the carbon in pig iron to get steel. Why do we want to do that? Why not just using pig iron with high carbon content?
Be a very brittle material.
Exactly. Last time, remember, the more carbon we have in a steel, it has higher strength but lower ductility. We don't like to have a lot of carbon. So to do that, you are using a different furnace, basic oxygen furnace. And oxygen will react with carbon, it gets the extra carbon out in the form of CO2, and then you are going to have steel. And the scrap metal is going to go through a similar process in the electric arc furnace. Since you have seen the video, I hope that you can visualize all of these steps. It is easier for you. And finally, you have the steel. You need to get the products that you want. And most of the products that we are interested in, they are being hot rolled. But there are other sorts of production. Again, you have seen it in the video. So you are going to have continuous cast, or you are going to have hot working. So with that, we can actually move to the steel properties. So I thought it's good to, how many of you are fans of Steelers? 3, 4, 5, 6, 7. I guess the rest are Eagles fans or neutral. Yeah, so I guess this semester Eagles fans are very empowered by Super Bowl, but in any case, so that also shows the role the steel industry plays in PA. Just the name of the Pittsburgh team. So I thought that's just to have this. Yeah, of course the steel part is, yeah, anyway. So, structural steel. What we are most interested in all types of steel is, of course, the structural steel, because we are either civil engineers in this class or architecture engineers. And it turns out that it is the third most used construction material. Concrete is number 1, then it's asphalt, because there are millions of miles of road. And steel is not something new. Iron ore has been recognized by humans many years ago. And then iron played a big role in the Industrial Revolution, and steel was a later development. So, what do you think if you would compare steel as a material, if you want to choose steel versus concrete, let's say, what do you think the main differences are? construction. Let's think about it. And you can say it.
Well, I was just thinking because concrete's a really weak contention.
But you can put reinforcement in it.
Well, it's still steel.
That's
Steel is a lot, excuse me, concrete's a lot heavier when it comes to the amount needed to produce the same amount of strength.
exactly. Good points so far. Any other difference between concrete and steel as construction materials?
Concrete and asphalt are made on site, and steel has to be made in factory.
Exactly. So it turns out that I was not as creative as you are. So the main difference between them that I've listed here is pretty much following what your friend said. Also, every other point that was mentioned is also valid. One very main difference between steel and concrete is that you make them on site. Most of the time, you can also have pre-constructed concrete elements. And this is kind of being transported, so it's off-site. In other words, as civil engineers, we can control all the properties of concrete and asphalt pretty much within reason. But steel pretty much comes in a catalog. So you buy it from a plant. In most typical projects, you cannot define or design your own steel. So this is one major difference. But everything else you said is also valid. It's true that steel is much better intentioned, concrete is weaker. It's true that there is a steel in concrete. And it's also true that for the same strengths, a steel is much lighter. And it's more expensive also compared to concrete. In any case, steel is used in a lot of different applications in construction. So I know you are juniors, but I guess you have seen girders and beams at some point in your life. Maybe? Yeah? So these are typically hot rolled and continuous cast steel. You are using them as load-bearing structural elements. And then there are fold form, like this cladding, these sheets that you also use in different functions in construction. This is a building, I forgot which building. This was in construction at State College. Right now it doesn't look like this anymore. This is a few years back. So if you go to any construction site, especially if the skeleton is made of steel, you can recognize a lot of steel elements. Where else do you think steel is being used? A little bit less obvious. Let's say when you look at a bridge in Pittsburgh, since we have a lot of Steelers fans, you see all these bolts and, I forgot, is it an Andy Warhol bridge? You can see the big bolts when you walk over the yellow one. Is it called Andy Warhol? Steelers fans from Pittsburgh? Yes. So fastening products, bolts, nuts, rivets, they're made of steel. We just mentioned that inside concrete, the reinforcing elements are made of steel. And there are all other kinds of steel elements which you can find in a structure. So steel is an important material. One thing that everyone in this class has to know is that steel is an alloy of which two materials, namely? Iron and carbon. So we all need to know for the rest of our life that the steel is an alloy of iron and carbon. You will see that there are some other alloying elements, but they're at lower percentages depending on the application. But this is pretty much it. And here, when you look at kind of the grand scheme of things, it's under ferrous alloys, so steel is here. And then when we say low alloy, it means that the percentage of alloying material is low. And under that, a structural steel pretty much falls under low carbon or medium carbon steel. Because, why? Why we don't like to use very high carbon steel in the structure? Yeah? Exactly. Because it's pretty. Now, steel has a lot of favorable properties. Relatively, the cost is fine compared to the properties. Iron is abundant, etc. But there are two major problems with the steel. One is corrosion. Corrosion, I don't know if you, sometimes if you look at the structures around you, again, today it's all about the steel and the steel that you expect. If you look at the bridges, and sometimes you see the steel or the reinforcing the steel, you see completely corroded. Have you noticed ever something like that? So corrosion is a major problem. Another problem is fire. At high temperature, what happens? Exactly, you use yield strength. So the yield strength becomes very low at high temperatures, and then the material can fail. So these are the two main issues with the steel. So the main sentence is steel is the alloy of iron and carbon. Everyone in this class is doing that. If you have higher carbon, steel strength will be higher or lower? I'm emphasizing higher. Ductility? Lower, exactly. And how about modulus of elasticity? It turns out that modulus of elasticity doesn't change much if you change the amount of alloy. And the reason is the amount of alloy is very small. It doesn't really change the interatomic forces as much. So the modulus of elasticity, you can think that the stays pretty much the same. And here in the side note, we'll get back to this again, but just remember to have an idea. The structural steel, you have very small amount of carbon. It's like less than 0.3% carbon. And it gives the ductility. I'm so sorry. Ductility. And if you have more carbon, material becomes more brittle. And cast iron, you may have heard of it. Cast iron is very high carbon. It's very high strength, low ductility. Now this is just to remind you that why we are going to have the same elastic modulus, because these interatomic forces are not going to be that different. So elastic modulus won't be that different if you add more carbon. And this is the effect of alloying. This is just a review. I thought to have it here if you forget why we have higher strength when we have more carbon. Because the alloying element do not let the slippage to occur very easily. I like this factor example. I feel like it's easy to remember when you think about it. And here comes again this really important diagram. So we are looking at percentage of carbon. So this is carbon. And you see how a stress-strain diagram is changing. You see how much I'm emphasizing this. Higher carbon, you have higher strength, lower ductility. Ductility is measured as percent elongation. So you see that it's shrinking. However, the modulus of elasticity is the same. This is not very obvious in this figure. So I thought us we could do a simple exercise together. So imagine I ask you to draw the stress strain diagram for two steel. One has 0.1% carbon, the other has 0.6%. We know three things. Modulus of elasticity is the same. Higher carbon, higher strain. Higher carbon, lower ductility. So let's see if we can draw these two diagrams. There is a reason I'm asking you to do that. And try to make sure that you are showing the initial part nicely. I want to see how you draw it. Talk to each other, please, work alone, discuss it.
Joe, are you just drawing?
Draw a stress strain diagram for two carbon content. Imagine I asked you this on Monday. Very probable. How would just qualitatively, how would the stress strain diagram of one look like? I'll try to show the beginning a little bit better than in this. I can see. Great. So, if this is 0.1%, it's relatively low carbon, so you have a nice. The reason I wanted you to do this is that, so this means they both have the same elastic modulus, pretty much. This one has higher strength. And lower ductility. Why is it moving? Okay. So yeah, the reason I wanted you to make this plot because this beginning of here is not really clear, and it's kind of important when you see these three differences between the two cases. Okay. Now, it turns out that in molten metal, depending on the temperature, you can have different phases. You have seen this before. This is kind of a reminder slide. I showed you this before. If you have different temperature, the alloy of iron can have different microstructure. And then it has different phases. Normally we use Greek letters for that, like alpha or delta. And this gamma is called austener. Now, there is a concept which I like you to pay close attention. It's very simple, but it's kind of maybe very new to you. It's called phase diagram. So people have developed these diagrams to see for a certain amount of alloying, let's say here carbon, material, at what temperature, what type of phase we have in the molten mix. So what does this mean? This means that if, for example, you have 3% carbon at 600 degrees centigrade, then you have basically these two phases, alpha plus Fe3C. If you have 4% at a different temperature, then you have a different phase. That's why it is called phase diagram. L in the phase diagram is the liquid. This is the molten metal when it is in the liquid state. So people have measured these, and you have these kinds of phase diagrams. Again, one axis is the percentage of the alloying element, the other is temperature. Maybe the best is to look at this example, an example a little bit later, then you can kind of get a better sense of what is going on. Why this matters to us? Because these different phases have very different properties. You are looking at two different phases of iron. One is ferrite, and the other is austenite. And you can see that microstructure is completely different. And these different phases also, depending on the microstructure, they have different characteristics. If you have, for example, more Fe3C, then you have higher strength and less ductility. Now, in FE exam, sometimes there are questions about this, and I think these questions are very good for us to understand exactly what phase diagram is. So let's start with this one. So we are looking at a phase diagram. Here is it's an alloy of two elements, alpha and beta. So you see percentage of alpha and beta, and it sums up always to 100. And here is temperature in degrees centigrade. So what does it mean? At every point, if you know how much of each material you have and at what temperature, you kind of can say what state the material is in. For example, if I have 40% beta, 60% alpha, at 1400, everything will be molten liquid. Now, the question is, at what temperature will a sample composed of 20% alpha, 80% beta begin to melt? Work on this together. Try to examine the phase diagram and see if you can figure it out. So 20% alpha, 80% beta. The question is, what is the temperature when it needs to melt? It starts to melt. This is very important in a steel production. Please look at the phase diagram. It's good. I think most of you have the idea of phase diagram, right? And this is kind of the purpose. So if you look at 20% alpha, 80% beta, this is this point. If we increase the temperature, the line will go vertically up, right? We are increasing the temperature. As long as we are below 825, it is a solid phase. Alpha plus beta, they are both still solid. Okay? The moment we pass 825, it begins to melt. Because alpha starts to become liquid, it begins to melt. And this is kind of what it is looked for here. If you wanted to see when it's completely molten, and some of you had looked at that, that would be this temperature when it transitions from beta plus alpha to N, which is a higher temperature. probably around 1500. So here it begins to melt. Now, the second question is a little bit more interesting. We change the color. So you have now 80% alpha, 20% beta. So the point is here now. And the temperature is given 900. So we can just find it here. So it falls into alpha plus L. There is a solid phase alpha and liquid phase L. The question is, what is the percentage of solid? Try to think about it a little bit before I give you the answer. So it has now alpha plus L. So it is some solid kind of floating in some water. quickly, now the way to think about it is, here the temperature is constant. Okay? So if we were here, it would be, what would be the percentage of solid phase? 100%. If we were here, it would be 0%. The temperature is the same, it's 900. We are somewhere in between, but we are closer to solid or liquid. Solid. So you could guess it to be just 60%. But you can also look at these numbers exactly and calculate this ratio. And just say that, okay, it is closer with the ratio of 15/25, which is 60%. I have a nicer, so you can just look at those 2 points. So here is 10, here is 35. So the ratio is 15/25. And then you get the number. But intuitively, you can also just guess it.